In the previous section, we looked at how do we add vectors together. So a natural question might be, is there such thing as taking the product of vectors? And it turns out there's more than one way to do that. In this section, we're going to talk about something called the dot product. And so the way it's defined is that if you have two vectors, A and B, then the dot product of those vectors is to take the x components multiplied together and then add the y components multiplied together. And then if we're talking about vectors in 3D, then it's the same idea. X is multiplied plus the y is multiplied plus the z is multiplied. So understand, though, that what's on the right side of this formula is a number. So the dot product of two vectors does not give you another vector. It gives you a number. All right, so we're going to talk about, what this dot product means, what it can do for us. First, let's just do a couple of examples to make sure we have the hang of the mechanics of it. So in example 1, they want us to take the dot product of A and B. So that means negative 5, 3 dotted with 2, 6. So that means we're going to take negative 5 times 2, and then we're going to add 3 times 6. So as we said, this is going to give us a numerical answer, not a vector. So make sure that when you take a dot product, you don't end up with any kind of vector notation down here. It should just be the number 8. And then we can, of course, do the same thing in 3 dimensions and with our ijk notation. So here, if I take A dotted with B, then 4i plus 6j minus 7k, I'm going to dot that, oops, sorry, wrong. There we go. I'm going to dot that with 3i minus 7j plus k. And so what that means is that I'm going to multiply the two numbers that have i's on them plus multiply the two numbers with the j plus multiply the numbers with the k. All right, and so what we get here is negative 37. All right, so that's just kind of the mechanics of how we go through and take a dot product. So let's talk about some properties that the dot product has. So first of all, you should note that the dot product of a vector with itself is just the magnitude of that vector. Okay, and so of course that's coming from the fact that if A is equal to A1, A2, then if you dot A with itself, it's just going to equal A1 squared plus A2 squared. But that's just the magnitude without the square root on it, right? So that would be the square of the magnitude. The commutative property holds for dot product, so doesn't matter what order you do the dot product in. The distributive property works for the dot product as well. And then you can do the associative property with scalar multiplication in the dot product. So in other words, if you have a constant times a vector and then you dot that with v, it would be okay to just dot u and v and then multiply through by the scalar. Or you can multiply the scalar by v and then take the dot product. And then finally, anytime you dot a vector with the 0 vector, you get then the number 0. So notice this here is a vector because it's in bold. This one is not in bold, so that's just the number 0. So we have one way of computing the dot product. It turns out there's another equivalent definition for the dot product. And so what we can say is that if you have the dot product of A and B and you know the angle that's between those two vectors, so you know this angle right here between A and B, then the dot product is the magnitude of A times the magnitude of B times the cosine of that angle. And at first that might be a little surprising, but I put a little proof down here, and this proof just uses trigonometry. So let me clarify. There we go. So what you do is you start by setting up this picture, and this vector here that goes to there is a minus b. Okay, that's what this vector right here is. And to kind of convince yourself of that, if I do a minus b, that's the same as a plus negative b, right? So if you go up a and then you go negative b, that puts you right there, which gives you this vector here, which is the same as this vector up there. So that makes sense that this is a minus b. So now what I want to do is I want to take its magnitude and square it. Well, if we're talking about the magnitudes, right, the lengths of these, then what we have is a triangle where you can use the law of cosines. So if you remember from trig class, if you do the side opposite of your angle, then if you square it, it's going to be equal to the square of one side plus the square of the other side adjacent to that angle minus 2 times those two sides multiplied together times the cosine of that angle. All right. And then on the other hand, you can also think of it like this. The magnitude squared we know is something dotted with itself, and with that I can FOIL things out. So if I FOIL out, I get the magnitude of a squared, magnitude of b squared, and then the middle of this minus 2ab. So taking the right side of this one and the right side of this one and setting them equal, and doing some rearranging, and notice, right, that is on both sides so they can go away, that's on both sides so they can go away. You end up with this, and if you divide by -2, you end up at the dot product theorem. So that's also a useful formula for us. All right, so let's see an example of where this can be used. It's not the only example. All right, but what if we're asked to find the angle between two vectors? Okay, what I'd probably have us do first here is let's go ahead and sketch what these two vectors look like. So I'm going to do this to start with. So 4, -3. And then 1, 2. So you can see what we're kind of expecting to get is an angle that's, maybe near 90 degrees somewhere. Kind of looks close to a 90-degree angle. So what we just learned is that A dotted with B is equal to the magnitude of A, magnitude of B, cosine of the angle between them. So that would be this theta that's in here. All right, but we can compute the magnitude of A, right? It's the square root of 4 squared plus -3 squared, which is 5. And we can compute the magnitude of B. So square root of 5. And we can compute A dot B. Right, so that's 4, -3 dotted with 1, 2. So that would be 4 plus -6, which is -2. So this becomes -2. This becomes 5. This becomes a square root of 5. And then cosine theta. But of course we can just divide both sides by 5 roots of 5. So -2 over 5 square roots of 5 is the cosine of theta. I'm starting to run out of space here, but then that means theta is equal to the cosine inverse of that, -2 over 5 roots of 5, which is, when we put it in degree mode, 100.3 degrees, or in radians, 1.75 radians. I'm going to separate this out here. And so just like we were predicting, we get an angle of about about 90 degrees. So, what did we do there? We just divided by the magnitude of A and B. So I didn't write it out, but, certainly if you want to kind of think of it this way, you can memorize this as a formula. But it's just, remember the formula that we learned on the previous page and just solve and get theta all by itself. Okay, so one other vocabulary term we need to start talking about when it comes to the relationship between vectors is what happens when we have a 90-degree angle between vectors. It's going to turn out that that is incredibly important to a lot of the future work we're going to do. So the term we use is orthogonal or perpendicular if two vectors have an angle of 90 degrees. And if two vectors, well, I should say it this way, two vectors are orthogonal or perpendicular if and only if the dot product is 0. And the reason that that's the case is because, just think about, what does theta need to be in order for this whole side to become 0? Well, 90 degrees, right? The cosine of 90 degrees, or the cosine of pi over 2, is 0. So that's the way we can tell if two vectors are orthogonal or not. All right, now in our notes here is kind of this little blurb about hitting a pitch, right? So if we consider a baseball or softball player hitting a pitch, sometimes the player hits a line drive. In a line drive, most of the force of the ball is just in the horizontal direction, right? But other times the player hits a fly ball. In that case, more of the force is directed upward than with a line drive. So one of the things you might want to know with vectors or forces and things like that is in what direction are those forces being applied, okay? And really, if you talk about how hard a ball is hit, you kind of need to know something about direction, how much of the force is horizontal versus vertical to know whether it's going to be something like a home run. Right, so that leads to this idea where we want to talk about basically how much of a vector is heading in a particular direction, right? And be thinking about force, right? Like, so how much of my force is headed in a particular direction? So we're going to introduce this idea called the scalar projection of one vector onto another, or another way of saying it is it's the component of one vector along another. Okay, so the way to describe it is this. Suppose I have this vector A, and then I have a vector B here. What I can talk about is how much of B is headed in the same direction as A. And I like to think about it as what kind of shadow, if there was a light source up here, what kind of shadow does B cast onto A? Right? In other words, how big is this? Okay. Well, the thing that I would have you remember real quick is that when we were just talking about vectors, right, just in isolation, this is the vector u, remember that the x component, if we made an angle theta with the x-axis, was u cosine theta, and then this one was u, magnitude of u, sine theta, right? So the idea was the angle between the x-axis, right, and the vector times the cosine or sine gives you the x and y. So now if we know the angle between these, it's the exact same formula. So you take the magnitude of b, but you take it times the cosine of that angle, and that's going to give you the component of b along a. Just like you can see in the picture, this is kind of the component of u, this is, along the x-axis. Now, this formula here, the b cosine theta, or magnitude of b cosine theta, can also be written as the dot product of a and b divided by the magnitude of a. And the reason for that is, you can see down here. Here's the given formula. If I multiply the top and bottom by the magnitude of a, then what occurs on top is I get my definition for the dot product from the dot product theorem. And so that's why we can use this. So the way to remember it is the vector that you're doing the scalar projection onto is the one that shows up more in that formula. All right, so let's do an example here and kind of get a sense for what's happening. So we have the vector C and we have the vector D, and it says find the scalar projection of D onto C. To use the notation that they taught us, that would be we would say it like this: it's the component of D along C. So the little one here is the one that you're projecting onto, essentially. So remember what we said is that this is going to, the C is the one that's going to appear more, right? The dot product on top, and it's, oops, in my eraser here, and the magnitude of C on the bottom. Okay, so we can write this out on top, right? So we've got 10, 4 dotted with 3, -2. All right, which is, and then, sorry, that's all divided by the magnitude of C, so 10 squared plus 4 squared in the square root. So that's going to be equal to 30 plus -8, all divided by the square root of 116. So 22 over the square root of 116. And let's also get an approximation for this. So 22 over the square root of 116 so about 2.04. Okay, so let's understand what this means. I can sketch these real quick. So this will be, I'm just going to do a real quick job of this. X component of, we'll call this 10, call this 4. So there's my C. And then D is over 3 down 2. So that's my D. And so the idea here is I'm finding the projection of D onto C. So imagine a light source down here shining on it. I project that straight, or I project that directly to there. And so this little red along C, that's what we just calculated. Okay, so that's the 2.04. This red that's right here, and sorry, I probably should have made a bigger picture, obviously, than that one. Let's see just a little bit better. Do something like that. Okay. So what we're saying is this is a length about 2.04. All right. Now this leads to what we call the vector projection of one vector onto another. And the only difference is, instead of talking about the length of that vector, we're talking about the actual vector. So it's just taking basically that shadow that's cast by one vector on another and actually making it another vector. So all you're doing is you're taking the scalar projection, right, which is this one. That's the one we just did. And then you're taking the vector you're doing this along and you're multiplying by it divided by its magnitude, and understand this is a unit vector. So the reason they're doing this is to, this part is the length of the vector. And so when you apply this vector here, you want it to be unit length so that it retains this length you just calculated. And so that's why this gives you the vector projection of one vector onto another And so here's how it all shapes up, where this part of it, all this stuff is just, right? That's all scalar calculation right there, essentially, times your vector A. So that's our vector projection. So we use PROJ for projection of B onto A. And just like last time, the one that you're projecting onto is the one that shows up all the time, and the one that the B is not showing up very much in the formula. So that's a good just memory device to keep in mind there. All right, so let's do an example of this one to make sure we feel comfortable with it. So it says we have the same one, C and D. Find the vector projection of C onto D. All right, so remember, and so I guess what I could do is I could start with that and multiply by C over its magnitude. But let's just start from scratch so you can see how that formula works. So here when I write it out, so the projection of D onto C, right? C is the one that's going to show up a bunch, right? So it's going to be C dot D over the magnitude of C squared times the vector C. So 10, 4, dotted with 3, negative 2 over the square root of, now, of course, we know the square root's going to go away, right? Because I am squaring it. But I'm just trying to be complete for this example, but if you could just drop it if you wanted. And then this is times the vector C. So on top there, you know, we've already done this, 30 plus negative 8. On the bottom, we know that that turns into 116. So we get 22 over 116 times the vector 10, 4. And then we can go ahead and distribute that through. So it's, you know, 220 over 116, and then 88 over 116. But I can do a little bit of simplifying here. And so when I simplify, this is going to give me 55. That's when I divide by 4. Oops. And here I get 29 and 22. So 55 over 29 and 22 over 29. Okay, and not to go and redraw the picture, but what is it we've done here? All I've done is I've gone back to the picture we drew here, saying that this has a length of 2.04, and then I've turned it into a vector. So this vector from this picture here is what we just calculated. So this is that red vector. All right, so the last topic in this section is we want to talk about one particular application for the dot product. Certainly not the only, but it's one you may be familiar with. So we're going to talk about work being done, right? Or another way of putting it is energy output. All right, so we know that if a force of magnitude F moves an object a distance d, then we can calculate the work done as force times distance. And, you know, depending if you've done some physics, you obviously are going to be really comfortable with this idea. But the reason work or energy is work is a measure of energy, is force times distance is if I have to exert a lot of force but only for a little bit of time, I don't necessarily spend too much energy. But if I have to expend that force over a lot of time or a lot of distance, it's going to take a lot of energy. So, you know, if I have to push a car like that's broken down 10 feet, then I don't have to use very much energy. But if I have to push it 3 blocks, right, on a slight uphill, then I'm going to expend a ton of energy. I will have done a ton of work. So that's our definition for work, is force times distance. So when we're asked something like in example 6, find the work done by a person pushing with 90 pounds of force on the back of a car. If the car has moved 40 feet, then it's as simple as this. Work equals 90 pounds times 40 feet, which is equal to 3,600 pound-feet, and that's going to be our pound-feet's one of the units for distance. Now here's the deal. Oftentimes, when you apply a force, you aren't able to apply all of the force in the direction you want to go. So, like for example, think about a lawnmower, right? When you are pushing a lawnmower, some of that pushing is going kind of downward, right? It's not all going in the same direction the lawnmower is moving. So in other words, not all of your force that you're applying is helping it move in the direction you're going. So it's not just force times distance. What we really want to say is that we need to know the component of the force that's going in the same direction as our distance. So the component of F along D. And remember, we talked about that. We said if theta is the angle between them, then that's going to be force, the magnitude of the force times the cosine of theta, which rearranged is the magnitude of force, magnitude of distance times the cosine of theta, which we know is the dot product. So the more general way to talk about work is to say it's the dot product of your force and your distance vectors. So let's take a look at a couple examples here. All right, so example 7 says a child pulls a wagon on a level ground by exerting a force of 20 pounds on a handle that makes an angle of 35 degrees with the horizontal. Find the work done in pulling the wagon 100 feet. Okay, so we know that work is going to be the force vector times the distance vector. Okay, and I'm going to show you 2 ways that you can go about this problem. Okay, doesn't really matter, but either one is going to rely on this picture here of, okay, the wagon I know is going in this direction, so there's my D, but I also know that the force is making this 35-degree angle with the distance vector. All right, so on the one hand, I could say that this is going to be force magnitude times distance magnitude times the cosine of theta. And I know all of those things, right? The child is exerting a force of 20 pounds, and the distance is 100 feet. And we can take the cosine of 35 degrees. So that's 1,638.3 pound-feet of work that the child has done. Now, we can do this another way, though. If you want to do this component-wise, you can say, okay, work is force times distance, or force dotted with distance, excuse me. All right, and so that's going to be equal to the force vector in component form dotted with the distance vector in component form. And the distance vector, of course, is just 100 in the x and 0 in the y. And then the force vector here is just 20 cosine of 35 degrees, 20 sine of 35 degrees. Oops, almost didn't give myself enough room there. Which is going to be equal to 200 times the cosine 35 degrees, which of course gives me the exact same answer as that. So you can approach that either way. You can either say, let's write out in component form what we're doing, or we can just use our dot product theorem formula. All right, one other example here. It says a small cart weighing 100 pounds is pushed up an incline that makes an angle of 30 degrees with the horizontal. Find the work done against gravity in pushing the cart a distance of 80 feet up the incline. Okay, so again, starting with the picture is probably a great idea. So here's my incline that we're talking about. And that incline's making 30 degrees. Okay, but let's draw our vectors, right? So our vectors are the distance vector, right? And then the force vector. Now, of course, they talked about the force against gravity, didn't they? So since I'm doing the force against gravity, I'm going to draw my force like this, right? That would be working against gravity. So just to kind of outline the two ways we can do this, on the one hand, I could say this is magnitude of force, magnitude of distance times the cosine of the angle between them. That would be this angle. But we know that angle, right? If this is 30 degrees, that's got to be 60 degrees. So we could say that this is 100 pounds of force, and the is the magnitude of the force, times, what's my distance? 80, times the cosine of 60 degrees, which is a half. So 100 times 80 times a half, and that gives me 4,000 pound-feet. Okay, and then just to show you the other way, I don't care how we do this, but if you say I'd rather kind of figure out the components, then you can definitely do that. So my force component is 0 in the x and 100 in the y, right? Because I'm going against gravity. Then my distance vector is going to be 80 cosine of 30, 80 sine of 30, which is going to equal 8,000 sine of 30 degrees. And at first you might say, oh, we're definitely getting something different here, but no, because sine of 30 actually is the same as the cosine of 60, right? It's a half, so we're still going to get 4,000 pound